Okay, thank you. Yeah, thanks to the organizers for this opportunity to come and present this work. I also like to acknowledge a lot of help I had early in my career from the applied math group in the department here at UCLA. Really helped me out in those early years. So I'm going to talk about device level modeling. And I'm going to talk about fuel cells and then lithium ion batteries. The fuel cell work is, I'll say, historical. But I wanted to present it. There's a number of reasons. Maybe I should admit part of it is just nostalgia. This was a really fun project. It's where I first got to work with Keith Promislow. That led to a long friendship and collaboration on many different problems. But I also noticed no one so far has talked about fuel cells, so I can at least tell you a little bit about how they work or how they worked back when we did this work. And also there is a common theme in the device level modeling that I'll talk about, which is mass transport is important, and that there are opportunities to make reduced level or reduced dimensional models of the systems, which both lead to more efficient simulation, but also focus in on understanding the important coupling in these systems. That's common to both of the devices that I'll talk about. And the third thing is, I guess, to say that all the other work that we've heard today really could lead to the new materials that then you can put into these higher macroscopic models. And at least in the work that I've done, there's a gap still. And the sort of the models that I start with and then make multiscale up to device and larger device levels are all empirical fits. And so filling that gap, I think, is an important thing to do. Okay, so I'm at the University of British Columbia. It is a great place to do applied math. So if you are a student or someone looking to come on sabbatical or take up a faculty position, you will find a good home there. I know I have. Okay, so the fuel cell stuff, again, historical. There's two review articles. One basically Keith wrote, the other I wrote, and then from these articles you can see what we thought was important. And it's different. And the project was really aimed at multiscale modeling stack level fuel cells. And again, we're taking empirically fit component models, and I'll show you the details of that. And we had this intense industry collaboration, which was great to motivate us to look at the right problems and also to do experiments that we could use both to develop and fit the models and then validate them afterwards. So it was really fun. Okay, so here's some pictures. Look how young and happy we look. Yeah, it was a good time. And this was a key collaborator in the company. And you'll see that we followed this advice. The models I'm going to show you, certainly for the fuel cells, it's going to be a cartoon, okay? And then I'll show you, that it wasn't just a cartoon, all the other stuff we added. But I think it's important just to see something relatively straightforward that you can follow in a 50-minute talk. Okay. Oh, whoop, I don't want that. Okay, what did I do? I did. Okay, so fuel cells, this is the sort of structure of a Ballard Mark 9 fuel cell from the time. And the dimensional aspect that I talked about, you can already see from this picture. These things are 1 meter long, right, with gas channels running in the X direction. So these are different than batteries, right? There's no kind of fixed charge in them. You just flow reactants through, and you can have continuous power as long as you've got, a hydrogen tank, that's not empty on the outside. And so you've got air flowing through these channels. You've got hydrogen flowing through these channels. This is not to scale. The air comes up and goes through a cathode material that I'll show you in more detail up above. There's a membrane, which was Nafion in the time that we were doing this. On the other side, you've got hydrogen, right, that also has a diffusion layer and reacts, making protons that cross over, react with the air and generate water. And so water management is an issue in these things. For the membrane to work properly, it has to be hydrated. But if you generate a lot of water here, you can flood this electrode, and that's sort of double-edged sword that happens in these devices. Okay, and if you think that this is a couple of millimeters, and the cell length is 1 meter, you can already see that there is going to be an opportunity for a dimensional reduction, which is, you take snapshots, 2D snapshots at different places down the channel, and you take whatever kind of fluxes that come out to adjust the channel fluxes. And so a 2 plus 1D model is not 3D, right? That's a pretty rigorous thing you can do. There's a guy called Mark Sikanel at the University of Alberta who's spent a bulk of his career working on a package that does exactly that. Well, okay, going back to Jean St. Pierre, we said, well, let's not do 2 plus 1. Let's just average out across this cross-section and just take a one-dimensional kind of cartoon of transport in this direction and couple it to a channel flow, another one-dimensional thing. But just to show you that there is more complicated stuff going on, here you can see, okay, I've switched the top and the bottom, unfortunately, in this picture. I'd forgotten that. You've got the hydrogen coming up, you've got the oxygen coming up, water forming, and then this Nafion layer, catalyst, and I'll show you some more details. Here's the membrane. This is an ancient cartoon of what the membrane might look like. I wanted to show this, though. This is something which was early, let's say, tricky phase field modeling of activated polymer materials that Keith started, and has led to all kinds of interesting modeling and for me, computational problems in the years to come. Anyway, this is basically material that's acid on a stick, right, in this thing, and so it has to be hydrated to make it proton conducting. There's this material called the gas diffusion layer, which is teflonated carbon fiber paper. So you have to get the current out, so that's the carbon fibers. It's teflonated to help with water management. And then the actual electrode material that they had at the time is a complicated mix, right? It's a mix of some Nafion, some carbon particles on which there are even smaller platinum particles embedded. And as I say, I am going to have an empirical fit to all of that complicated structure. But I wanted to show these 3 slides of all of this because we're talking about stochasticity. And another aspect which hasn't really been in the forefront at this meeting, though, is there's a bunch of stochastic materials that are used in electrochemical devices, right? And so to get average properties from these kind of things is an interesting problem. Okay, I don't think I have to say much here, right? Okay, you've got hydrogen oxidation, oxygen reduction. Those are the main reactions. And now you can imagine through all of that complicated, channel-to-channel activity, modeling that from first principles is not going to work. So now, at least as a thought experiment, imagine that you have a small piece of that whole membrane electrode assembly with channels on either side. You put it in a button cell, and you do a bunch of local experiments to see crossover, polarization curves at different conditions. And then you take those and you do an empirical fit. Okay, and so here is the sort of thing that you get. This is cell voltage that you get as a function of current density. And you just throw in something that's like this. So there's a standard sort of Butler-Volmer term. And then there is a term that involves mass transport, right? So this would be the term that says as you draw more current, you have to get oxygen, right, from here all the way, through this gas diffusion layer. You have to get it dissolved in the ionomer, and it's got to get to a catalyst site before it can do anything. You could pretend that that was just a linear diffusive process, in which case you'd get a term like this, okay? Of course, this term is larger than just gas diffusivity over that length scale because of all the other things that are going on. Okay, and then of course the membrane resistance, or this resistance, is larger than the membrane resistance because there's also all kinds of other things going on. Oh, you got a question already? Okay. I thought you'd wait until I had a potential. And then you would ask
But I see the potential already. So I never understood, I'm seeing this a lot. Like can you give me a very simple explanation for this log as a ln I over I0? What is it?
It's a
chemical potential drop.
I'm going to say it's a Butler-Volmer term. It's just something that describes this drop accurately. Of course, it doesn't work as I goes to 0.
Yeah, I'm always wondering, is it an electrostatic, let's say? Or is it a chemical potential drop? What is it?
I'm just going to say Butler-Volmer and turn it over to the electrochemist.
Okay.
Is that okay? Can I do that?
Okay.
Okay. It's an empirical fit. Yeah. That works quite well. Okay, so now I'm going to tell you about this cartoon model, which is just going to be a cathode only, no water management, isothermal, constant pressure. And so what you've got is, remember, there's this dimensional reduction. You've got this, 1 plus 1d. And so what happens is you've got some channel fluxes that decrease with the current, which is dependent on the distance you are down the channel. It's not uniform. From the flux, you can get the channel concentration, just assuming that you're starting with regular air as input, which is 21% oxygen. And then the other dimension, the +1 dimension, is just the simple empirical fit in this cartoon that I'm showing you now, right? And so the problem is, someone tells you the S, that's the stoichiometric flow rate. So this is it's a dimensionless flow rate, which is you can figure out the flow rate you would need to generate the current that you've specified, and S is just a multiplier bigger than 1 that tells you how much extra you're putting in. You can't use S equal 1 because of mass transport limitations. You would have no oxygen at the outlet, which means you couldn't be drawing any current there. Right, so this is the global problem in this cartoon. You're giving some operating conditions. You're telling it how much current, And then what is supposed to come out is, in this scenario, in the unit cell, it's going to be a constant voltage. So imagine you've got, big copper plates on either side of this unit cell, so that's keeping the cell voltage uniform. But the current will vary. That will lead to changing flux, and that changing flux leads to changing oxygen concentration, and it's all coupled together. And what has to happen is you have to generate that average current. And I'm originally a computational guy. Oh, there's a question.
Yeah, I didn't understand, so you said your flow controlled your oxygen concentration.
Yeah.
How does the current come back to, so the current?
Oh, so the current is telling you how much the flux is changing as you're going downstream.
Okay, so that's how
Right.
much, it's basically the
And then this
oxygen
is like an ideal gas law thing that says if you know how much total concentration there is, right, then as this decreases, the oxygen concentration will go down.
That's just at the,
Yeah.
near the
Yeah.
interface. Right, okay, two sides of the condition.
Okay, we're good?
Yeah.
Okay. So anyway, like I say, my original background is computational, so it's like, okay, here's a kind of a funny, non-local problem. How do you compute it? Anyway, it's pretty straightforward. Keith mocks me that I count equations, so I'll make him count equations with me. You can think of having, n grid points down the thing. So you've got 3n and then the scalar u, 3n plus 1 unknowns, right? You've got n equations, each one of these. So you've got 3n, and then this average current is what actually specifies u, even though u is not in that equation. So it's a big nonlinear, non-local problem, but you just do Newton's method with continuation if you need. I had a workshop that I gave to a bunch of undergraduate students in Spain. So there's a bunch of notes that's written up, and this code, if you think that this is a fun problem for your undergraduates to look at, you can find it. It's on the website in the underneath the talk slides. Okay, and this is what comes out, right? So you can vary the stoichiometric flow, and as you reduce it, of course, the cell voltage goes down slightly. But more importantly, the current distribution changes, right? If you're running at low stoich, then it really wants to draw more of the current at the beginning when the oxygen concentration is high, and then it really is decreased at the end. And you can go down to 1.05 more or less, and below that, the cell fails. You can't draw that. You can't draw that current. Okay, so I said, one of the things I wanted to show you is, this is a common themes in electrochemical modeling at this level. Three things. There's a dimensional reduction. There's mass transport, and there's sometimes the necessity to use empirically fit models, even though, of course, I think everyone wants to be able to provide those for new materials without experimental testing. Okay, so what's the next thing to do? Well, remember the goal was to do stack level modeling. And so let's talk about stacks. So it's basically these unit cells stacked up. These plates then get called bipolar plates because they're the anode on one side and the cathode on the other side. And so the same total current goes through each cell, right? But you could think of, okay, I haven't talked about thermal effects, so no end cell effects. But you could think that, in fact, the conditions could vary between these cells. And that's one of the things that the company was interested in knowing was, what kind of tolerances do you need to have in the headers to make sure you have some uniform conditions. So again, we're at the level of a cartoon. It's still no water management, cathode only. But you can see that these plates have, it's all, you have to do the scaling, right? But they have non-trivial, non-negligible resistance to in-plane currents. And that means the cell voltage can vary in X. And of course, now there's not just one cell, there's a bunch of them indexed by M. Okay, and there's a story. You know I'm Canadian, and we're supposed to be modest, right? And I came up with this name for this relationship, which is a pretty simple one to set up. I call it the fundamental voltage equation, right? And so this is an equation for the voltage, right? And if you think of the in-plane currents as, you know, I don't know, voltages divided by resistances, right? Then this is some sort of semi-discrete problem for the cell voltages. Okay. Anyway, so it's kind of fun. And this lambda you can scale and get something called the Wagner number. This is the same Wagner as in the talk this morning, but the length is scaled out, so it's actually a dimensionless number. Okay, and why I gave this one such a fancy name, Keith knows this is coming. I had done all of this work setting this up, and I had come up with a dimensionless parameter W, and you know what my last name is, right? So I was really hoping that this would be, you know, the Wetton number. And then someone said, oh, the inverse of your number is this Wagner number. So not only was my number stolen from me, but I had to change everything that I'd written up to 1 over W. So this W is really like a ratio. I won't get the sign, I won't get the ratio right, but it's the ratio of equivalent electrochemical resistance to sort of transport current. Okay, and with this W, you can, if you take a sort of a representative number, you can get a handle on how many adjacent cells are affected by a current anomaly in a cell. Anyway, you can code this up, and this is the sort of thing that you get. If you had it's symmetric, so it's a 13 cell stack with an anomalous cell in the middle, which I've indexed as m equals 1. And I'm going to put a lower flow rate in that cell, right? So it is going to struggle. It's going to want to put more current at the beginning than at the end, because you saw that in the unit cell things. But this is the sort of funny pattern that you get. We have, you know, experimental validation of these kind of models. So I'm just showing you the results of this simple one. And you can see this would be the base case if all cells, you know, were running uniform, right? This is what it would do. But this is the effect of this one anomalous cell in the middle. Again, the current density is sort of uniform at the beginning and then does some crazy stuff at the end. And if you look at the voltages, you see that this poorly fluxed cell, you know, the voltage really crashes near the end. What's interesting is then the outlet voltages nearby are raised, and this is something that the engineers called the volcano effect, right? This low dip and then this kind of shallowly decreasing thing, and they were pretty excited when we could reproduce this.
Excuse me.
Oh, yeah.
Is that anomalous cell, is it that there are some variations on the layers or where it comes from?
No, it's just that the inlet flux of that center cell is lower than the rest. Right? So if you went back to the unit cell model, we're putting this low stoich in the middle, right? And if the plates were infinitely resistive, then every cell would just behave independently, right? But they're not, right? There is right? A penalty to having different current densities than your neighbors, and this is what comes out. And then this is another little code that's on my website if you wanna play with that. Okay, now I didn't want you to think that all we did was cartoons, so I'm just going to show you a few other things. So we put in the anode, which runs in the cells that we were looking at counterflow for water management improvement. And so we put in water management, which requires temperature. There's a much more detailed membrane model. And these are the sort of things that we could then do. We could capture water crossover accurately to experiments. Yeah, the line is us and the dots are experiments. We could capture liquid water formation in the cathode catalyst. I've got so many stories to tell, and I don't know if I want to waste time on science, but we had these results. We were presenting them at a meeting. And it was a meeting with some other companies that were there as well. And they said, how did you get these measurements? And so, you know, as a mathematician, you don't know, like, what is a technical secret and what isn't. So we asked the Ballard people, and they said, no, don't tell them. Don't tell them what they do. Anyway, they referred to this as chop data. And so what it is they run the cell, right? It's a specialized, cell. And then they
being recorded.
I think it's long enough now that it's safe. And then they would take out the membrane electrode assembly. They'd freeze it, and then they'd cut out little circles, and they'd weigh them to see how much water was in it. It did not seem like a technical secret to me, but okay. And yeah, so then we looked at the effect of cathode humidification. This was, of course, not ideal, right? Because it's an extra system component to humidify inlet gases, and so they didn't want to do that. But you can see there's some a real performance dip if you didn't. And this was near the end. We started looking at some corrosion issues. This is a really subtle one. You can see that the current density, so a typical current density for these cells is 1 amp per square centimeter. So this is a really low current. So you're idling, right? And it looks like you've got, stoichiometric flow rates, that are high. But remember, if you are at this low current, then the actual flow that you're putting in is very small, right? And so then what happens is on the hydrogen side, there's a crossover of hydrogen gas from the anode to the cathode. And that hydrogen just burns when it gets to the cathode catalyst, right? So it's a direct combination. And if the flow rate is high, then that crossover rate is basically negligible. But at these low flow rates, even though you put in more hydrogen than you needed, in fact, you run out at some point because of that crossover. Right? Okay, and here's the potential. It's a potential. I'm just waiting for everyone to jump all over me and ask what this is all about. All I can say is that this is something that they measured with so I'm not showing the experimental results, I'm showing the model results, but they measured this with a standard hydrogen electrode. Okay, and I hope no one asked me more than that. Anyway, so what happens here is then all you have on this side is oxygen that's crossed over to the cathode, which means the anode potential goes up, but you've still got a nice positive voltage, and so that means the cathode potential also goes up. And now you're basically, you're running the reactions in reverse. And these cells aren't designed for electrolysis. And so at this high potential, you start getting carbon corrosion. Okay, so that's the sort of thing that we could look at with these kind of, remember, quite simple cross-plane averaged models with coupled to down channel stuff. Maybe I'll just skip over this. There's a bunch of other things that I did, electrochemical modeling. And again, this is the perspective I wanted to give you, is as a sort of an intermediate before theoreticians can really characterize these materials. This is what we did, right? Was to take simple experiments to fit heuristic local models of the complicated stuff that it was not easy to model from first principles. And then take those locally fit models to couple to physics at the macro scale, well understood physics, right? I mean, we've got linear resistivity in these bipolar plates. We've got fluid flow down a channel, and that's laminar. So these are all things that are easy to do. And then, of course, in this project, we had the luxury that then they would do experiments to validate what we had done. There was a scenario when I would be here for the whole time, but I'm only here this week. But you don't need me because you've got Keith, who can tell you about these models. And then if you want to compute sort of specific things, you've got Jürgen Fuhrmann, who in the same sort of time frame was looking at these kind of questions as well. So I'm redundant, is what I'm saying. Okay, let's go to batteries. I'm going to describe something called the pseudo two-dimensional model, or the Fuller, Doyle, and Newman model of these batteries. And again, I'm going to do it in a sort of cartoon way to show you the structure of the model, which hopefully gives you some insight into what's happening. Now, these are models that are, if you look in the literature, you can see that they are needed to correctly describe battery behavior at high C rates. I don't know if you guys know what a C rate is. So it's a semi-dimensionless, so it's a semi-dimensionalized current density, and it's a C rate of 1 is the current that you would draw that would drain your battery in 1 hour, right? And so if you think of your phone and you were using it constantly and it lasted 10 hours, then on average that would be a 0.1 C rate. If you charge it up in an hour, that's a 1 C rate. If you drained your phone battery in 6 minutes, that would be a C rate of 10. Now, I don't advise that, okay? Don't do that. But there was this, I didn't have a company that I was working with or experimentalists, but there's just a sort of a question that came up as we were looking at these models, which is, well, so what current rates are high? Okay, and so that's the question that I'm going to answer with this simple model that I'll show you. Okay, so you've had battery tutorials, so I won't say much. There's this graphite side where the lithium hides inside, right? And then there's this more expensive, fancier side where the lithium intercalates, and that's energetically favorable, right? That's what makes this whole thing work. And then there is this, and we've had some talks, this really complicated electrolyte, right? Which for me, not in the model I'll write because it's even simpler than that, which for me is called X minus, because you just don't know what all is in there. Okay, and so in discharge, a lithium ion comes out, goes through the electrolyte, and goes into one of these, intercalates into one of these particles on the other side. Okay, and again, the P2 model is a reduced dimensional model of this process that includes mass transport, right? So it's exactly the same kind of flavor as what I've talked about already. Okay, I'm just going to make it's not necessary, but I liked it. Okay, I'm going to make a simplification where I'm going to line up all of these particles in a line, and I'm going to squish them together into a slab, right, with the same length scale that the particles have. Okay, trust me, it's okay. You can do this and still get something sensible. So here you go, right? So now I've taken a representative average of this whole thing. I've squished all of the solids together, and it's then going to be a repeating structure. And I've left the electrolyte space with the characteristic spacing in between. Okay, and so by this time, I knew how to do actual asymptotics, right? And so there's the first thing, which is the size of the solid particles is much smaller than the cross distance across this electrode. And so I'm going to think of the electrolyte as a one-dimensional process, right, in this direction, coupled with a one-dimensional intercalation diffusive process in the other direction. And if you look at the numbers of the different transport properties, this is a reasonable thing to do. And of course, not my idea, right? This is old news. Okay, and so now you can do some scaling, right? So again, you have to sort of shut your eyes a little bit to believe that the process of lithium, intercalated lithium in the particles is a linear diffusive process. But remember, I'm only taking that as a 1D in this particle slab. And then you've got, again, the electrolyte is way more complicated than a dilute, right, thing. But I'm just going to take that as an approximation, or as a cartoon, maybe I should say, right? And that's only in the x direction. And then, of course, they get coupled together at the interface with the term that you've already seen. Okay, and then you can do some scaling, right? And what you end up with is two mass transport limiting factors. You can think of drawing a certain current density. And you can scale that to the diffusive flux in the particles. So that's from the edge of the particle into the interior, right? Okay, so there's one thing that you could scale the current density to. The other thing that you could scale the current density to is, well, you have to, get through the electrolyte, you have to get the ions, back and forth through that electrode. Okay, and I'm going to tell you now that the P2D scaling is that all three of these currents have to have the same magnitude, more or less. Okay, so now I'm going to have some dimensionless parameters. I'm going to scale the current to this diffusive, particle diffusive limiting current. I'm going to scale it to the ionic current, right? And I'm saying that if either of these is small, then you don't need this fancy electrochemical model. You can do some reductions. Okay, do you care about this? Okay, you can get some scaled equations. Okay. Here's something you can actually do rigorously. This is a former student who got us together to work on this problem. I can say that this is one of my life's great achievements. The Irish government paid for me to go to Barcelona for 2 weeks. I think that was pretty special. So here's the thing, right? you can see in battery literature, this kind of wealth of models that you need to describe a battery. And at least if you believe this starting point, if you have a current that is not mass transport limited by either of these things, then you can reduce this model to an equivalent circuit model, right? So you can do something very simple. Okay, so if they're both not small, then you need the P2D model. But now there's some other things that can happen, which is you are mass transport limited by one, but not the other. And then you can end up with two different reduced models. Okay, thank you. So one is something called the single particle model, which is quite often used. And so now you can understand the scaling that justifies that. There's another one which I've never seen in the literature, which means maybe this is just never happens for real batteries. But that's one where the electrolyte is the limiting factor, but not the particle diffusion.
For solid.
Oh, for solids?
For solid electrolyte, we use that.
Oh, okay. Oh, okay. Oh, there you go. Okay, now the actual P2D model has not the slabs that I've done. They've got, at every point across the electrode, they put a representative spherical particle, right? And so that just changes some geometric effects, right? Instead of this, you've got some spherical stuff. And then you should also include some tortuosity in the electrolyte transport. So at the cartoon level, it's not different than what we had before. Okay, so I took this simple cartoon. I just want to show you with some visual things of how these different regimes behave. Okay, so now you have to imagine that this is the positive electrode. I'm just looking at one electrode. And I'm discharging. And so I am trying to get lithium ions from this side into that side. Okay? Right? So I'm pushing. The electrolyte has to push them, down. Right? And then I've got these particle concentrations. These are the intercalated particles. Here's the outside of the particle, and here's the particle center. Okay? So here I am, I'm pushing lithium I'm pushing lithium this way, lithium ions this way. And now you can see the story, right? Of course, I am diffusive. I'm limited by diffusion this way, and so I build up a higher concentration of intercalated lithium here, right? And I'm also transport limited this way, right? And so I have a higher lithium concentration here than here. Now the interesting thing so this would be high current, right? The interesting thing about it's all scaled, right? But it would be high current. The interesting thing about this is you can't really talk about state of charge because the cell will fail while you still have lots of capacity left because you just run out of room at the surface to intercalate more things. So that's really the fundamental thing that you get with the P2D model that you don't get with all of the other models that you can have. Okay, so I'll show you a couple more pictures. So here is the single particle dynamics. Remember, that's where the diffusion in the particle is limiting, but not the electrolyte. Right, and so now you can see, there isn't really any variation in this direction. So why not just put one blob, right? One particle that describes this whole thing, right? And then, okay, and apparently this works for solid. If you want to see it the other way, so the particle diffusion is really good, but it's limited by the electrolyte, right? Well, then, this particle is all full, right? But it's different from its neighbors because it's the transport this way that's limiting you. Okay, so I think I've got across what I wanted to cross, and no one really complained about my potential. I guess I avoided that. I wanted to tell you about these ideas of macroscopic device-level simulations, and then some of the things that can happen, right? You can get these dimensional reductions. I compute things. I'm happy when the thing to compute is easier, but I think more importantly, it just gives you more insight into the coupling that's important in these devices. Also, some strategies for when to do physical modeling and when to say that's too complicated, right? And to say to collaborators in industry that they just have to give you some stuff, right, before you can move on. I showed you this was really quite a cartoon model, but having looked at that, you really understand the structure of this model. And one of the things that people want to do is to put more realistic electrochemical models in battery management systems, which then you want to do real time, and you want to do control, which means you're doing more than just real time. And so you want to run these faster. And so there's a couple of ways you can do that. There is I don't think anyone in the audience, maybe Jürgen might be interested in this. Yeah, sorry, now he's looking up now, right? Sorry, Jürgen, I didn't mean to pick on you. It's basically a fancy numerical linear algebra approach to an implicit time step for the P2D model. This is an archive paper that will never get published because the student left, before that happened. And then, of course, there is an intelligent way to do machine learning for these models at high current densities, which will get published. We're just working on revisions to a paper. Okay, and I'll end there. Thanks for your attention.